Hi, my name is Mason Avidano, and today I'll be walking you through some manufacturing techniques and strategies that I think are vital to optimizing the manufacturing process as a whole and also promoting a manufacturing economy. To really stress the importance of optimizing this manufacturing process, the U.S. Department of Defense estimates that U.S. manufacturers as a whole contribute almost $2.35 trillion to the overall U.S. GDP. For the purposes of this project, I've selected just a few specific manufacturing techniques and strategies that I really think are the most vital in facilitating this manufacturing economy. So these start all the way at the design process with design for assembly and disassembly, and continue all the way to the manufacturing stage with various machining processes and those automated inspection tools we use to check their quality. Also, we'll take a look at the manufacturing process as a whole with Toyota's lean manufacturing strategies. Before the physical manufacturing process even begins, engineers need to choose some design considerations for a project. And of these, I think the most vital for consumers and manufacturers is design for assembly. So assembly is a more general term, corresponding to a wide variety of any design considerations. So these include things like the product's part count, the type of fasteners used to connect different components, even the symmetry of parts, as well as their ease of handling and ease of insertion into any slots, as well as any secondary operations like tightening or gluing parts. So with this in mind, why do I believe that design for ease of assembly is vital? Well, 70% of the product's overall cost is determined during this design and development stage. So eliminating any unnecessary parts here would drastically reduce the cost burden on the company and the consumer. Basically, any parts that don't have to be included don't have to be designed or manufactured. Also, parts that are optimized for assembly reduce the mental strain and physical strain on assemblers. And for consumers, products designed with these built-in fasteners and minimal parts are really durable and easy to repair at home. Some specific uses of this design for assembly methodology include modularity, where products with similar parts and easy to assemble fasteners let consumers have a great deal of customization and control. Also, built-in fasteners like deformable plastic latches eliminate any need for screws, bolts, and glue, and reduce any excess strain on those assembling a product in the manufacturing setting or even at home. Also, symmetrical parts like perfect cylinders can be slotted right into place without the need for extra thought or additional time. However, design for assembly can sometimes be limited by being slightly theoretical. Even the best designed plastic fasteners and clips are always still susceptible to tolerances. Also, combining these parts to limit the part count can create components that are maybe hard for the design for manufacturing methodology. Design for disassembly, in my opinion, is just as important as its previously discussed counterpart. This quote from a Dassault Systems brief on the topic of design for disassembly really emphasizes the amount of manufacturing waste that we put into the global environment in an effort to produce more products even quicker. Designing for disassembly allows a product to be easily broken down into its individual components. So these components can be reused in another product or even replaced to get the original product back to working order. So with this in mind, I really appreciate design for disassembly because these products designed for disassembly won't have to be scrapped and added to the ever-growing levels of manufacturing waste. Also, cleanly breaking down a product with design for disassembly and reusing these parts requires less energy than recycling the materials into completely new components. So designing for assembly can actually be more environmentally friendly than designing for recycling. However, sometimes designing for assembly is difficult, even more so than designing for assembly. So by the time disassembly is actually considered, the product will have already been distributed far outside this centralized manufacturing or company location. So corporations have way less agency over the product and how users can actually return it to be disassembled. With those design considerations out of the way, it's time to move on to manufacturing processes. So through my research work at Georgia Tech, I've really come to appreciate the benefits of machining. Machining is an incredibly broad set of processes, and it's likely that any consumer would recognize at least one. So some examples of machining processes include turning, where a workpiece is turned while a stationary cutting tool removes material. Milling, where a rotating tool moves on multiple axes to cut a piece. That's commonly seen in CNC machines. Drilling, where a drill bit cuts a hole of constant diameter into a workpiece. And tapping, where a tap cuts threads into a workpiece with an array of sharp teeth. Machining is the manufacturing process category of choice for my work and research because it really allows for this extreme dimensional accuracy and a wide variety of geometric features. Also, it's widely used and sometimes may be the most economical choice because of it. But most of the time, machining wastes material cut from the workpieces in terms of chips or shards. And it may not be successful in certain applications like other manufacturing processes are. So for example, that tapping process we mentioned earlier produces threads that are noticeably weaker than those formed with rolling. Although machining may be known for its high accuracy, it and any other manufacturing processes are still always susceptible to error. So to examine the quality of these manufactured parts, automated inspection really stands out as this agile and advanced form of product testing. Automated inspection is often grouped with destructive testing options like tensile tests and non-destructive testing practices like ultrasonic inspection and radiography. But automated inspection's connection to these learning algorithms and very precise sensors allows for a greater connection between the manufacturing and the testing processes. I find it really important that parts can be inspected during the manufacturing stage, and feedback from that inspection can be put back into the manufacturing controls to make sure any mistakes are corrected within the loop. Still, automated inspection is expensive to start up and maintain, and may be more susceptible to error when compared to the more traditional testing and inspection methods, just from the precision required for those digital sensors. After the design, manufacturing, and inspection stages, we're really ready to look at production as a whole. So lean manufacturing methodology, as developed by Toyota, provides, in my opinion, the best framework for optimizing this entire manufacturing process. Lean manufacturing focuses on the concepts of muda, mura, and muri. Muda, or wastefulness, means not using any systems or resources to their full potential. Muri, or overburden, focuses on overburdened systems and people when production is not evenly distributed. And mura, or unevenness, refers to production being limited when times of high demand are not predicted and accounted for. So why has lean manufacturing grown past its start in automotive manufacturing? I think lean manufacturing is incredibly vital because it provides this widely applicable algorithm for locating specific sources of weakness in the manufacturing process. Also, lean manufacturing covers the entire manufacturing process. Even product transportation and delivery can be optimized with muda, mura, and muri. On the same note, any product can benefit from accounting for these general principles outlined in lean manufacturing. However, considering only lean manufacturing when addressing any kind of manufacturing optimization may have some pitfalls. So just for starters, lean manufacturing doesn't provide as many concrete or actionable solutions for addressing these sources of weaknesses that can be found when applying the mura, muda, and muri strategies. Also, lean manufacturing is sometimes too idealized. It doesn't really take into account all the intricacies that affect the various lean manufacturing strategies. So for example, decreasing waste may increase the unevenness found throughout the system. As we've traveled from the design process to the manufacturing and inspection stage, and finally to lean manufacturing in the continuous improvement segment, it's really become clear that manufacturing is a juggling act of a wide variety of considerations. And while I've only scratched the surface of this wide variety of design and manufacturing methods, I really hope I've been able to convey how vital this process is, not just for engineers and business people, but also consumers. In this manufacturing economy, there's nothing more important than knowing how our goods are produced and how we can optimize this process to better serve humankind and our planet. Thank you.